In this short video, I'll talk about a uniform distributed loading and its point of action, and why the point of action has to be located at the center of the plate. So here's a drawing of the horizontal plate, and it is hinged at x equal to 0, and x-axis is measured from the hinge. And as you can see, there is a uniform loading. So P is uniform, and its dimension is basically a force divided by area. So it can be some stress, it can be some pressure, but what's important here is that this P is uniform, meaning that it's constant, uniform and constant. And if you look at from a perspective view, this is the plate having a length of L and width of W, and here is the hinge, and x-axis is measured from the hinge. Therefore, the area of the plate, entire plate, is W times L. Here, what I'm trying to show is that the point of action of an equivalent force or net force to this plate is located at the center. So here is the x equal to 0, and x-axis is measured from the hinge. And what I'm trying to say is that there is this net force, F, which is the P times area, P times the total area. That's P times W times L. And what I'm trying to say is that its point of action is at the center of the plate in the x direction. So these two setups are basically equivalent as far as moment balance is concerned. Okay, how can I show this? We follow the same step as what we did in hydrostatics. So we think about a infinitesimally small element, and its width is just like our hydrostatics class. Its width is dx. So on the sketch on the right, so basically we have this infinitesimally small area element, and its area is dA times W dx, because its width is dx. So what I'm trying to do here is to evaluate the moment due to the uniform distributed loading to this infinitesimally small element. I'm trying to argue that as far as the moment balance is concerned, these two systems on the left is equivalent. So then how much force is applied to this dx element? So here is my element, and its width is dx. And on the top surface, I have a force applied to the uniform loading. Its loading is P, its area is dA, and dA is W times dx. So this is the force applied to the top surface of this element. So then the next thing we want to do is that we want to measure the moment of this force dF with respect to the hinge, which is at the x equal to 0. Therefore, the moment arm of this force is x, which is the location of the small element. So this x is the moment arm. So if you draw this moment arm vector and the force vector, so that their origins coincide with each other, then you use the right-handed rule for evaluating the moment, and it's a clockwise direction. Therefore, this is the negative moment. Use your 4 fingers to align and align your four fingers on this plane, then you will be able to see that this is a clockwise moment. So then the moment of the force dF is, it has a sign of minus, and moment arm is x, force is dF. So this is the moment of the force dF generated around the hinge. So then minus x p times w times dx. Again, loading p is constant, with w is constant. So this is the moment generated on the small element. What is the total moment generated around the hinge? That's a simple integration of this moment on the entire surface, entire plate. That's going to be integration of minus x pw times dx. Integration variable is x, and x runs from 0 to L. And all the constants can go out of the integrals. So integration from 0 to L, x dx, and minus pw. Integration of x is 1/2 x squared. Integration from 0 to L, minus pw, 1/2 L squared minus 0. Therefore, this is the 1/2 pw L squared. So this is the total moment due to the uniform distributed loading around the hinge. So then what about the second equivalent condition setup, which I'm showing here? So what is the total moment generated by this force F around the hinge? So if I take a look at this case, then the moment of F with respect to x equal to 0, you can easily calculate that. Its moment m sub F is, its moment arm is still, it is L over 2, as we argue. And as you can see, it also creates the negative clockwise moment, minus L over 2 times F, and minus L over 2. The net force is P times W times L. Then I rearrange these terms, PWL squared. So this is the moment generated by the net force F applied at the center of the plate, which is equal and identical to the moment generated by this uniform distributed loading. So therefore, it shows that instead of the trying to find out evaluate all the integral, you can just place the equivalent net force at the center point of the plate.